Hi everyone, I'm Wenju Sun. I'm a PhD student of Beijing Jiaotong University. The title of the paper I will introduce today is Decoupling Learning and Remembering, a bilevel memory framework with knowledge projection for task-incremental learning. In this work, we take inspiration from the human multi-level memory system and propose a bilevel memory model for incremental learning, which consists of working memory, long-term memory, and knowledge projection. The working memory responsible for new knowledge learning to ensure high plasticity. Long-term memory in charge of storing learned knowledge to guarantee high stability. And the knowledge projection is a bridge to connect these two memory units. Next, I will describe our work in detail. I will divide this report into four parts, which are introduction, methods, experiments, and conclusion. The first part is introduction. This work focuses on incremental learning, which is the ability to continually learn new knowledge while keeping the memory of old knowledge. Clearly, incremental learning is important for models applied to an ever-changing environment. To achieve incremental learning, most existing methods follow the structure as the figure A, which maintain a memory to store old task information. However, the information in memory only serves as a reminder, and the model is in charge of both learning new task knowledge and maintaining old task knowledge. The limited model capacity will lead to a plasticity stability trade-off during the incremental learning, which is the plasticity stability dilemma. In contrast, human brains are known for both high plasticity and stability for incremental learning, owing to its multi-level memory system, as shown in the figure B. It consists of a short-term memory and a long-term memory, where the short-term memory only maintains temporal information for decision-making, and the long-term memory stores all the learned knowledge inspired by the human memory. This paper proposes a bilevel memory model with knowledge projection, which is BMKP for incremental learning. This is the framework of our BMKP model. It mainly consists of three parts, including working memory, long-term memory, and knowledge projection. The working memory responsible for new knowledge learning to ensure high plasticity. The long-term memory in charge of storing learned knowledge to guarantee high stability. And the knowledge projection is a process that projects model knowledge of working memory into a compact representation and then stored into the long-term memory to achieve the high memory efficiency. A key challenge for BMKP is how to organize the knowledge between working and long-term memory. We define the knowledge as the ability to transfer a given input to the expected output. Therefore, we can see in the parameter of working memory as the knowledge represented into the parameter knowledge space. And we want to find a core knowledge space for long-term memory, in which the knowledge can be organized into a compact form, the basis of which could not change the output of the network, and we denote it as B, and the projected parameter into the CKS is A. The BMKP training process for task T consists of the three steps, which is knowledge memory learning, long-term memory updating, and knowledge projection. For the first working memory learning step, we encourage the working memory to learn new knowledge with respect to the pattern basis B with the following regularization. Therefore, the laws for working memory learning, including the cross-entropy laws and dysregularizer. In the second knowledge projection step, we first extend the core knowledge space with the new basis through the single value decomposition, and then project the knowledge from the parameter space into the core space. The final step is the long-term memory updating step, where the new knowledge representation and the basis are transferred into long-term memory. Besides, this step introduces a recommit mechanism to prevent the performance degradation due to the drop of some minor basis during the knowledge projection. To be more specific, we retrain AT in the core knowledge space with the training data. The third part is the experiment part. Here, we select several baselines and 3 datasets. The results show that our BMKP achieves state-of-the-art performance in almost all datasets. The next is the ablation study. We contrast the 2 variations as a comparison baseline. The result proves the effectiveness of the basis updating and retraining. Besides, the retraining is less important as it only refines the model performance. We now analyze the memory efficiency of BMKP. As can be seen, the larger memory ensures the higher performance of BMKP. More importantly, with the same memory usage, BMKP can perform the best accuracy on all 3 datasets, proving the memory efficiency of BMKP. The final part is conclusion. Inspired by the multi-level human memory system, we propose a bilevel memory framework for incremental learning, which benefits from both high plasticity and stability. We propose a knowledge projection process to project knowledge from PKS into compact representation in CKS, which not only improves memory utilization efficiency, but also enables further knowledge transfer for incremental learning. We design a regularizer to encourage the working memory to reuse previously learned knowledge, which enhances both the memory efficiency and the performance of BMKP. The experimental results show that BMKP achieves state-of-the-art performance in most cases with lower memory usage. That's all. Thanks for watching.